Hey everyone, this is section 3, and in this section we're going to learn how to draw molecules. So we call those Lewis structures, and in this way we can kind of visualize what they would look like in 3 dimensions, and then we can also tell when there would be multiple bonds, like double bonds or triple bonds in a molecule. So here's some examples of Lewis structures. We have drawn some of these earlier in the year. And with these, we're drawing those valence electrons, and then we're looking at where they're going to bond. And in this section, we're just dealing with covalent. So we're dealing with nonmetals, covalent bonds. That's what we're focusing on. And so here's like a definition. Lewis structures show how the atoms are arranged in a molecule. And we're trying to visualize it in 3 dimensions, and that can be tricky. We can use them for ionic and covalent, and we're focusing on covalent here, and we are only looking at those valence outer electrons. So here we have carbon, and it has 4 valence electrons, and then hydrogen has 1. And then here we're showing how water would bond, and then how ethylene would bond and make a double bond, and how acetylene that you might have used in a torch would bond with a triple bond. So here's how you draw them. I'll put the steps and then I'll demonstrate. I can draw on here with my finger, so we'll try that. So the first thing you do is you look at your molecule, you look at your formula, and you add up all the valence electrons. Remember, we're only looking at the outer valence electrons. And the next step is you draw a simple backbone structure just with single bonds, and then you look at how many electrons you used up by drawing that structure, and out of your total, how many electrons you used, and then you distribute the rest of the ones that are remaining so that all of the atoms have 8 electrons, which is that octet rule. We want them to have 8 electrons. And so here is an example with methane, which we've looked at before, and this is CH4. So the first step that we said was we look at how many total electrons we have. So I'm going to draw this over here. Well, that's big. Carbon has 4 valence electrons, right? So I'm going to write a 4, maybe. And then hydrogens, we have 4 of them, and they each have 1 valence electron, 1 outer electron, times 4. And so if we add all those up, we get 8, right? Man. Okay, does that look like an 8? This might be rough. 8 electrons to deal with. Okay, then we're going to make a basic backbone structure to draw this molecule. And we don't really know like what this is going to look like. We could draw it a lot of different ways, but usually carbon is going to be in the middle, and usually hydrogens are going to be on the outside, because hydrogens only like to have 2 electrons. So they're going to share. They're not going to be bonding to a whole bunch of stuff. They're just going to be on the edges. So remember that rule. Hydrogens are going to be on the outside. Carbon is usually going to be in the center at some point. So we'll draw a carbon here. And then I'm just going to do a basic backbone structure. So there's one H. There is another H. There is another H and another H. Okay, can you see that? So now we're going to count how many electrons we've used, and here we've used, I'll use my mouse, 1, I hope you can see that, 2, 3, 4, 5, 6, 7, 8, because each of these here is 1 electron. Carbon has those 4, and then hydrogen also had 1. And so we were basically sharing those. So this is kind of a sharing. And so there's our 8 electrons. Okay. So I'll go ahead and clear that, and we'll go to the next example. And it would be a good idea to draw these in your notebook. I should have said that to begin with. So let's do water next. Okay. So first step is we count up how many valence electrons there are. And here's our H. Okay, we have So let's review our formula. We can write our formula here is H2O. Okay, so we have two, each hydrogen has one valence electron, and there's two of them. Okay, and then oxygen has 6 valence electrons, right? Because it's in that 16th group, so it has 6, and that's going to add up to 8. So we have 8 electrons to distribute. And now we're going to make just a backbone. We already know the shape of water. We know that it kind of looks like a Mickey Mouse. It's kind of bent. And so we can draw the O, and we know this already, but we'll find out why. It kind of looks like this. So this is like our backbone structure of water. And we just used 1, 2, 3, 4 electrons here. So we can do this, -4, and we have 4 left. So we have 4 electrons to do something with. We know that our H's are happy because they only want 2 electrons. But right now our O has 4. It has its 2 and it's sharing 4. And so it's not happy. So with those 4 extra electrons, we're going to put them up here on these corners. And that is, that's the other 4. So we've used up all the electrons, and that's our Lewis structure. Okay. Another way to look at it too, and this isn't really the correct way to do it, but we already know that, like we said, oxygen has those 6 valence electrons. So you could draw them like this in this case. And then we have our H guy. Okay, and it has 1. Each of these have 1. And then here we are. This is where we're bonding. And you can see that we're ending up with these 2 bonds. And then we have these 2 up here. And these guys are called, lone pairs of electrons because they're just alone there. Those little electrons there. Okay, so that's water. And then, carbon dioxide we can draw. So again, we need to do our total electrons. Carbon has 4. And then oxygen has 6. I'm doing these from memory. 6, what was that? And we have 2 of them. So we'll go times 2. That was supposed to be a 6 there. Sorry about that. So that's 12 plus 4 is 16 electrons. Okay, remember what I said about carbon? So let's write the formula here. So we're all on the same page. Carbon is COO2. And that's why I had 2 oxygens there. And I said that carbon is usually in the middle. So let's draw carbon in the middle. And this is kind of like water. Water was H2O. We had our O in the middle, and we had 2 H's. And I told you it was bent because we knew that. But this one we don't really know. And I'll just tell you it's not bent. It's straight. So I'm going to draw my O's coming out like that. Okay, and here I've already used 4 electrons. So I have 1, 2, 3, 4. Okay, so I'm going to subtract 4, and I still have 12 electrons. And this is where things get a little tricky. First of all, none of these are happy. Our O only has 2 electrons, our carbon has 4, and this O has 2. So we have a lot of work to do. What we often start with, and I'm going to kind of play dumb because I know this isn't what CO2 looks like, but I'm going to start with loading this guy up with electrons. He needs 6 more. He needs 3 more pairs to have 8. So I'm going to put them on there. Hopefully you can see those little dots. Okay, I used all 12. I just used up my 12 electrons. I put 6 on each one. They're all gone. Now my O is happy. He has 8. This O is happy. He has 8. But my carbon only has 4. So this is not the right structure. So here's the deal. Whenever you run out of electrons, that means that you need to start doing some double bonding. So if that's a little rule of thumb, let's write that down. If you run out of electrons, start double or triple bonding. Yay. So I'm going to use my eraser. I'm going to erase those. This is weird. Okay. So now we have 12 electrons back that we get to play with. And now I'm going to, let's double bond this. Okay, so I used 2 electrons there. So I'm back up to 12. I used 2. And then, hey, let's throw a double bond over here. And this is where you just kind of get to play, kind of like balancing equations. So I've used 4 electrons. So I can go -4. And that leaves me with 8. Okay. My carbon's happy. My carbon has 8, but my oxygen only has 4. 1, 2, 3, 4. So what if I added 4 more there? Now it has 8. And if I added 4 more there, and I'm kind of distributing them on the corners so they're as far away from that double bond and from each other as possible. And so there I used 8, and that gives me 0 electrons. So there's my CO2. So that's how you do that one. Okay, now cyanide. And hopefully you remember the formula for cyanide is just simply CN. Isn't it? I think it's CN minus. Yeah, because it's a polyatomic. I'll know in a second if that's right. I'm pretty sure that's right. And now you'll see why our polyatomics are ions and why they have to have charges. So carbon here has 4 valence electrons. Nitrogen has 5 valence electrons. And then we have this extra electron. And here's the deal. If you ever end up with an odd number, when you're adding these, something's wrong. Something isn't jiving. So that's how I knew. I was doing that in my head and I knew, oh yeah, it's a minus. So we have 1 extra electron here for a total of 10, right? We have 10 electrons to deal with. And we only have 2 atoms, so we can just go bink, bink, and we're gonna have 8 electrons left to mess with. So I could just start throwing electrons on here. I could go 1, 2, 3, 4, 5, 6, 7, 8. But none of these are happy. None of these have 8 electrons. Like this guy has 6 and that guy has 6. So what do we do if we run out of electrons? We start double or triple bonding. So let's try that. And a lot of this is just trial and error. So I'm going to put a double bond. So then we used 2 electrons. We're at 6 left. And so if I kind of did this in my head, I could put 4 here and maybe 2 here, and I still wouldn't have enough because this one would only have 6. So I'm going to give it another bond, -2. You got to keep track of your little friends. Okay, I have 4 left. So then I can go 1, 2, 3, 4. Everybody has 8 electrons. Carbon has 8 and nitrogen has 8. And then we do this too. We put a bracket and a minus because overall that whole molecule is minus. And that's our whole Lewis dot for cyanide. Make sure you put a bracket if it has a charge, a positive or negative charge, you have to put a bracket. Okay, so those are some examples. I think there might be 1 or 2 in the book I'll grab in a second. And we also sometimes have resonant structures. And this is when there's not one right answer. There's a few right answers. And they kind of resonate between different structures. So I'll do this sulfite. Yeah, I don't think it's a 2-. I think it's just SO3. We'll find out. Okay, so S has 6 valence electrons. I'm doing this without a periodic table. I guess, where's my book? Where did I put it? Oh, here it is. Let me just check. S, yes, it's right under oxygen. It has 3 valence, and then oxygen also has 3, or 6, I'm sorry, and there's 3 of them in the formula. And so that adds up to 24. So we have a lot more electrons to play with here. And since it's SO3, S is probably going to go in the middle. So there's that. And I'm going to put my 3 electrons. Okay, so we have used 6. Okay, we have 18 left. Hang on, I gotta check something. I'm wondering, so take a minute and write that down. I'm wondering if this is supposed to be with a 2 minus or not. Let me just check it really quick. No, I don't think it is. Okay, so, so this is the right formula. So we have 18 left, and if we were to distribute those evenly between the 3 oxygens and put 6 on each, because 18 divided by 3 is 6, you would have a full octet. You'd have 8 electrons on our oxygens, but then our sulfur would only have 6. So if we don't have enough electrons, we start double bonding. So I'm gonna go ahead and double bond. And I've used 2. I have 16 left. And then on this one, I'm going to add 2 electrons. So that one has 8. Sulfur has 8. And then on this one, 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And I have now used all 16. So this is all fine and good, but here's the deal. This guy could also look like this. I could have put that double bond up top, and that is a totally different molecule. That is not the same thing. So I could have put them there and done the same electrons, 2 pairs on this top one. That's a completely different molecule. I'm going to put this in brackets. You have to put this in brackets. Don't not put them in brackets when we're doing resonance or when they're charged. Okay, so this is a whole different one. And then guess what? I could have another version. Ooh. And that would look like this. So I can have my S single bond here, another single bond here, and then a double bond here. Can you see that? And then I put my 3 pairs to make my 8 octet. Another 3 pairs, and then here I put 2. This is a whole different molecule. So that's resonance. You have to draw all 3 or all 4, or sometimes there's 2 resonance to show that these molecules can resonate between the 3. They can be any of those 3, and you have to draw all of those and put them in brackets. So that's how we do resonance. Okay. So let's look in your book at example 12.4, and we're going to do these in your notebooks. Let me find what page we're on. Where are we in? Section 3. Okay. Oh boy, there's 7 of them. Okay, so we'll go through these. Okay, so NF3. So this is let me write the page. 448. Page 448. Okay, so we have NF3. Okay, and we look at valence electrons first. And so we say that N has 5, fluorine has 7, and there's 3 of them. So 21 plus 5 is 26. Okay, so now I'm going to put my N in the middle and my F, and I always distribute these like spread apart as far as they can. Okay, you guys, so I've used 6 of them. I've used 6 electrons. I have 20 left. And where am I going to put those 20? Well, I know that my 3 fluorines are going to need 6 electrons each. And that's going to take care of 18. And then my nitrogen needs 1 pair. So I think I can just put all these electrons on right now. I'm going to put that one there. So that takes care of 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So that's all 20 electrons. And this is actually the correct way to draw it. These 2 lone pairs up here are actually going to push everything else down. Ooh, like this. And then you're going to put all your lone pairs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And so that's actually what it's going to look like. Okay. The next one is B, O2. Oxygen has 6 valence electrons times 2 is 12. So we have 12 to work with. I'm going to draw my 2 oxygens side by side, and I've used 2, and I have 10 left. So if I were to put 2, 4, 6, 10, 12, 14, I would have too many. If I were to put 6 on each of these, that would be a total of 14. So if I don't have enough electrons, I start double bonding. So I'm going to double bond. Now I've used 4. Hopefully what I said just made sense. If not, ask me. And then I have 8 left. And I want to satisfy the octet rule. I want to put 8 on each one. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And there's my 8 electrons, and that is O2. It's a linear molecule. Okay, next one is C, which is CO. Carbon has 4 electrons, and oxygen has 6. And so that's 10. Okay. So we're just going to draw this like this. I've used 2. This is carbon monoxide, by the way, toxic. Okay, so I have 8 left. And again, if I were to put 6 here and 6 here to make them both 8, I would run out. I don't have 12. So if I don't have enough, I start double bonding. And so then I used 2. I have 6 left. And I don't have enough to go 2, 4, 6, 8. So I'm going to do another bond. And then I have 4 left. I'm running out. Oh, sorry, 2. That's a -2. So I have 4 left. And I'm going to go 1, 2, 3, 4. Carbon monoxide. That's a lot like cyanide. Looks, I mean, not like actually, but it looks like cyanide. And the electrons are similar. All right, so now we're on D. And D is pH 3. I have a feeling this one's going to be weird. I haven't given you these rules yet. Okay, so phosphorus has 5, right? Has 5 valence electrons. And then hydrogen has 3. Okay, so that's a total of 8. Oh no, this one's not weird. Okay, so we're going to put the P in the middle. I'm just going to do it like this. So we're spreading those out and putting our H's. And I've used 6, already used 6. You like these easy ones. I have 2 left. Phosphorus is not happy. Oh, oops. What's going on? Okay. All right. Phosphorus is not happy. So I'm going to put 2 here, the 2 last ones. Now it's happy, but now that lone pair is pushing down those H's. So it actually looks like this. Dink, 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 H, H, H. Okay. So that's what pH 3 actually looks like. Okay, now for E. E is H2S. H has 2 valence electrons. And if this is easy and you're fine, skip it, I think. I think that's good advice. Don't skip it if you're not fine, though. We have 8 total. This one's going to look like water. It's going to be bent. So we're going to have S in the middle, and it is bent. I'm just telling you that so you don't have to redraw it. We've used 4 electrons, so we have 4 left, and here they belong, right, just like our water. So that's our 4 lone pairs, and those are going to push those H's down. Okay, next one. This one's a little tricky. This is a polyatomic ion, SO4, 2 minus, okay? And so S has 6, oxygen has 6, and there's 4 of them, plus we have 2 extra electrons. And so is that 32? Yeah, 32. We have a lot to play with. We're going to put S in the center and position our others like so. O, 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 O. I've used 8. 24 left. And then look at this. I have enough to put 6 on my O's. Okay, and we used all 24. Next one is G, NH4 plus. Okay, N has 5 electrons. And remember, whenever we're going to get an odd number here, 4 times 1. That's weird. And that means that we're going to subtract minus, this seems weird, but since we have a positive, minus 1 electron. So we have 9. This is 9. I'm going to take 1 away because we have a positive. So it's going to like cancel 1. So now we have 8 electrons. Okay, so then I'm going to distribute these. I didn't draw that at the right angle. It's kind of supposed to be like that more. NH4. And we've used all 8. So, and then if you have a charge, remember you put it in brackets and put a plus, okay? Then we have H is ClO3 chlorate. Some of these should seem pretty familiar because we did them before. We're just drawing them now and finding out why they have weird negatives or positives. Chlorine has 7 valence electrons and oxygen has 6 times 3 of them. This is going to give us an odd number. So we're adding 1 electron. We're adding that negative. 18 plus 8 is 26. Am I right? Chlorine's going to go in the middle, and then we'll do a little surrounding of oxygens, kind of cut it in thirds, and I've used 6. I have 20 left, and I know that chlorine is not happy, and so I could put 2 on chlorine. Now I have 18, and then I could go 2, 4, 6, 8, 10, 12, 14, 16, 18, and there is all of them. And so this guy would actually be like this and kind of have this pushed down shape, because that lone pair set is going to push those down. So that's actually the shape. And then we're going to put it in brackets and put a minus. Okay. Oh man, one more. So now we have I. I is SO2. I think we did this. No, we did CO2. Okay, so S has 6 valence electrons and O has 6 times 2. And so that is 18. Okay, so S, and this is going to look like CO2, I'm pretty sure. So I'm going to do it linear, straight line. I've used 4. This seems like a high number. Okay, and S is unhappy. O is unhappy, O is unhappy. But if we added 6 here and 6 there for our 12, we would only have 2 left for our S. And we know that if we don't have enough electrons, we start double bonding, consolidate. So I'm going to put a double bond here. And then that's 12. And then I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But here's the deal. This guy is a resonance because I could have put the double bond over here. Also, this lone pair is going to push down those 2 O's. So this is what it actually looks like. Okay, hopefully you can see all my little silly dots. And it doesn't have a charge. I don't have to put the charge. Oh, I don't know if I told you to do the arrows. This is sometimes how we see the arrows, or you can just do a normal arrow. Either way is fine. And then we're going to draw it the same way, except double bond on this little business end here. And put 2 electrons there, and then put 3 and put the brackets. So that's resonance for SO2. Okay. So now there are some exceptions to the octet rule. So it's not always true that you're going to get 8 electrons on each one. Some get more than 8, and those are called expanded. So these are weird cases, and I'm really sorry, but nature is like this, and we're just trying to make sense of it, and this is how the world works. So sometimes you're going to get more than 8 electrons, and sometimes it'll be less than 8. So sometimes it'll be 6, and sometimes you'll have weird, odd numbers and not pairs. So those are just things to be aware of. I don't think you have any in the book questions. But xenon, like one example, I'll just do really quick. XEF6 is one example. And basically you have a xenon with 6 Fs coming off. And then another example is BF3, like BFF. And that one's gonna, so that one has 12 valence electrons, which is weird. And then this one's gonna have 6 instead of 8. Oops, that would be Fs. So, yeah, so that's weird. And those are just some exceptions. Okay. So I'm going to close this and then I'm going to do section 4. And as, so what you need to do now, there are book problems. I'm sorry, I just closed my book. Let me flip back to that. So you need to do the book problems now. And you are going to take a picture of those and then upload them to Classroom. That would be the best way to keep these kind of organized. So you have page 449. We'll type that, how's that? Page 449, number 1 through 4. And then you'll have to upload those because that's not something you can type because you're drawing these, which is common in chemistry. If there's ever anything you can type, then go ahead and type them. So just upload that picture for that homework assignment. All right, see you guys later.